All right, welcome everybody. How's it going? Good. We're going to go ahead and get started. If you're just filtering in and you didn't get the full link to the page, we'll go ahead and start. We'll put that back up again. But we're going to go through the brief presentation we have first, and then we'll get into more of the coding after the fact. All right, so my name's Ryan. I am a transfer student from Saddleback College, so just down the road. I didn't go that far. But I'm in my last year here. I just started doing machine learning and AI stuff. I think it was about like May or earlier this summer. I got involved with Jason. We're doing some work over in physical sciences for machine learning research, mostly to do with anomaly detection, and that's been pretty fun. So I decided we'd join this club and see if we can't put on some workshops. But yeah, I'll let you.
Hello everybody, my name is Jason. Also senior year, CS and Business Information Management. I worked on a few projects. I worked, like Ryan said, at physical sciences for like anomaly detection. Also worked in like nano materials down in chemical sciences on a machine learning project. So we're just pumped to put on this presentation for you guys. So I hope you enjoy it.
Awesome. Okay. So if you guys don't already know how to play Flappy Bird, it was probably popular now, I don't know, it's been 2 years, 1 year, something like that. A lot of people know how to play. It's basically just a little bird that's constantly falling. If you tap on the screen, it's going to flap. The goal is to get through as many pipes as you can, increase your score. Obviously, if you touch a pipe or the ground, it's gonna fail, right? Game over. So what our goal today is to make an AI to be able to play this game without our interaction. So we won't actually have to press tap. It'll figure out when to do that for us. We'll go to the next one. So this is our plan of attack. We need to make the brain of the birds, right? Which is a simple Keras artificial neural net. And we need to ask a couple of things. So like, what are we going to look at to determine where to jump, right? Because otherwise it's not going to know when to jump. It's going to be randomly guessing. So it has to know what it's going to look for. And what design are we going to use? That's the other thing we have to look at when we're designing the neural nets. Also, we're kind of using this algorithm, the genetic algorithm, to kind of implement the idea of like evolution, right? So we have like the winners of the gene pool, whatever birds go the furthest. We're going to take the top two, and you're going to cross over and mutate like the genes or the weights. And I'll get into more of what that is in a second. But you're going to use those top two birds basically to spawn a next generation based off of those two birds, right? So we're going to watch them fail, and they're going to suck at first, and then they'll get better. So that's the goal of this that we're making today. So feature selection. So what are we going to use to base all of our decisions, right? So we need to select a few features from the game to do that, and so our parameters, right? So we look at the bird height. So at any given time, right, the bird is going to be X amount of units above the ground or whatever. And also the lower pipe, which is this one, the distance to the bird, so that's this arrow right here. And then we also need to look at the height of that lower pipe. So just 3 things is all we need in order to base our decision for this. Right. And do you want to go over this part?
Sure. So, like we said, the first part of the thing that we're going to build is the brain of the bird, right? We don't want to have to control this thing all the time. So we're going to use a Keras artificial neural net. It's kind of like the simplest version there is, and that's what we're going to use for the brains. I know a lot of you guys, or some of you are freshmen, so we have a small little video over here for you to explain what a neural net is. It's like a minute because we don't have a lot of time to do this stuff, so it's going to go over pretty quick, but it's going to show some like the main topics, all right? Oh, just so you know, the guy that invented Flappy Bird made $1 billion yearly for like the dumbest game on earth. So you guys come up with something, post it. So we're going to play this video super quick. And yeah.
Imagine a neural network as a kind of black box, which takes one or multiple inputs, like the sensors of a self-driving car, processing them into one or multiple outputs, like the controls for the car. The neural network itself consists of many small units called neurons. These neurons are grouped into several layers. Neurons of one layer interact with the neurons of the next layer through weighted connections, which really are just connections with a real valued number attached to them. A neuron takes the value of a connected neuron and multiplies it with their connection's weight. The sum of all connected neurons and the neuron's bias value is then put into a so-called activation function, which simply mathematically transforms the value before it finally can be passed on to the next neuron. This way the inputs are propagated through the whole network. That's pretty much all the network does. But the real deal behind neural networks is to find the right weights in order to get the right results. This can be done through a wide range of techniques, such as machine learning. However, that's a topic for another minute.
Coolio, that was like the quickest video ever. All the rest of them I found were like 19 minutes. I don't want to bore you guys. So we'll move on to the next. All right, so like I said, we're going to be using Keras. So there's two different libraries for Python that are like really helpful. And if you guys want to learn them, all power to you. So Keras is kind of like the upper layer. It's a little bit easier to learn, but it runs on top of a thing called Tensor Flow. So Tensor Flow is kind of Google's Python machine learning library, but it is kind of complicated because it comes with like a lot of random digits that you got to know, a lot of random inputs, a lot of random numbers. So Keras kind of moves all that stuff away and makes it a little bit easier for you to do the same thing a lot quicker. So learn TensorFlow if you can. Keras is a really great way to start. It makes it like so super easy to code. All right. So I don't want to scare you guys. This is some terminology that I might throw in while we're actually coding. I don't want to go over like too hardcore on what it is. Some of you guys might know what it is already. So I'm just going to give a quick overview. So when I mention that we're adding this in, you kind of know what I'm talking about, right? So ANN, like we said, is an artificial neural net. It just means that all the nodes, like you saw in that video, are connected to every other node. So everything is connected to each other, right? So we have to design this thing. It has an input layer of a certain amount of nodes, has a hidden layers, and then an output layer. And we'll design that here in a minute. The next thing they mentioned was the activation function, the thing that transforms the weights inside the nodes to the next one. It's kind of like just a function that squashes numbers into a certain range. But I don't want to go too far into that. If you guys want to read up on them, they're pretty awesome if you're all about math. Complicated, but fun. The next thing is the optimizer. So, like we said, we want the neural net to get better, and it uses the optimizer to do that. So we want to find the smallest amount of error between what is real, what the thing we actually wanted, and what the neural net predicts, right? So we want to decrease that error every time, and the optimizer is the thing that does that. So depending on what optimizer you use will show how quickly you get to the smallest error and how it gets there. But I'll show you some design. So another thing, design of a neural net is like totally an art form. You guys can put whatever you want in there to see what the best result is. There's no like standard. People say like, oh, you have to do it this way. You can do it however way you want, and in whatever way it gets the best results is awesome. And that's where a lot of research comes from these days. What is the best design and all that good stuff. So be creative. Next thing, once we've actually built our model, we're going to get like one that comes with some functions with it, right? So like the video said, the whole point is to optimize those weights and to get the model the best weights possible so we get the smallest error, right? And backpropagation is the way it does that. You guys can read up on it. There's a bunch of good videos, and if you guys want after the thing, I'll give you like a bunch of resources on where to find this stuff. Prediction, we're going to be using that. So prediction is like once your model's built and trained and it's awesome, you actually got to that point, you're going to give it a sample and then see what it thinks. You're like, here's a dog picture. Can you figure out if this is a dog? And we use the prediction function to do that. The next thing is called epochs. So this is during your training. So say, for instance, you want to predict housing prices and you have a data set of 50,000 houses. One epoch will be running through all 50,000. So if you say, I want to train my model over 15 epochs, you'll run through that data set 15 times. But we're actually going to avoid epochs. We're going to do something way cooler than that called a genetic algorithm. So Ryan's going to go into that in like a second.
Perfect. Thank you, Jason. So remember how I mentioned crossover and mutation? We're using that in our genetic algorithm to kind of come up with as generations go by, it gets better and better, right? So obviously this eagle is pretty jacked. It's probably going to go on father multiple generations, you would think, because it's very strong, right? So you want to select the strongest and the best to make the next generation. So in our case, top two are taken, ensuring the prime gene pool. Right now, a little caveat is sometimes when you're running this, you'll see one bird like go through and like go really far, but all the other ones like died at the first pipe, right? So obviously you get the one parent that went really far, but then like probably one of the other ones that didn't go that well. So the next generation may not be as good as that first parent, right? But eventually it'll get there. So that's kind of what you want to think about that. So crossover, right? So we have two genes. You have one from like your mom or from your dad, right? So you, when they made you, it's like you cross over like this. So it's either you get one of these, right? So it's half could be combined in this manner or in this manner, right? So in this case, maybe your parent, like your mom was super tall, or your dad was an awesome athlete. You'd be like, well set up to make your way to the NBA or something like that, right? That's the one way it could turn out. And the other thing we use is mutation. So you're taking a single gene and changing it by like a random amount. So you'll randomly change a part of a gene by a random amount. So it's not just the same one you're changing by a random value. It's just like randomly you'll change certain ones. And what this does is basically to add diversity to the gene pool, right? So if we didn't do this, what would happen is if you ran the program, it would still take the top two parents, but eventually those top two would like slowly narrow down. So all the 50 birds, because we use like 50 birds every time the generation goes through, so it's like 50 chances. They would eventually become like, they would act as one, so they'll like all balance at the same because they have like the same genes. So adding mutations adds enough randomness in it so that it kind of, you can get better and not just get the same, because otherwise if they're all the same, then they might just be like terrible, and that's not what you want. So adding the mutation is very key to this. So this is the part where you guys are going to just go to this link. If you haven't already set up the virtual environment, you want to give them like a couple minutes to do it, or do you want to just go in?
Yeah, so how many guys have actually set up the virtual environment, have everything installed, it's all good? Okay, quite a few of you. So we'll give you like 5 minutes just to follow this link. There's instructions for Windows and Mac and Linux and all that. You need Python 3.6. Doesn't work on Python 2 because Python 2 is shit. So 3.6 is the way we're doing it. We'll give you guys 5 minutes. There's a bunch of mentors around here. We'll come and help you if you get stuck.
Yep.
But we have a lot of coding to do, and all this is going to make a lot more sense once we actually get into the code, which is going to be fun.
Yep.
So let us know if you guys have any problems, and we'll come over and help.
Yep.
Okay. Hey guys, we're going to have to get started, otherwise we're running out of time. So if you guys have any problems, just ask your neighbor that already has it done. Ryan's going to help you too, because I'm going to be going through the code. But I'm going to get started, okay? So if we can kind of keep it down a little bit so we can hear. Coolio. All right, so I'm just going to go into my editor right here. I use PyCharm because it's fun. So everyone should have their Venv activated. I'm going to show you now how to do that. I have my Venv saved somewhere else, but I'm going to show you. So I have my Venv saved. Oh, I'm on my desktop already. So we're going to go. Coolio. And so you should have, when that little like the name of your environment is right next to it, means it's activated, which is great. And you can see if all your Python packages are installed by doing a pip freeze like this. And it should tell you that all of that stuff is installed and that's all you need. So I know a lot of you guys are having problems with that Tensor Flow 1.11. It only works on Python 3.6, and it's the only one that works for this because it's dumb. I'm sorry about that. But now we'll go into the code, and I'm going to show you, walk you step by step on all the pieces that we need to get this running, so you guys can actually start training your Flappy Bird models, all right? So from here, I'm just going to CD into my actual cool. So you should be able to see all these from the folder over here, okay? So now I've gone into flappy.py is the package that we're going to be editing. So whatever. Yeah, what's up, bud?
Can you make it bigger?
I can try. And then if I...
Also try to move it up, because back here is all the head up here, so I can't see it.
Like that? Oh, okay, got it. Is that a little bit better?
Yeah.
Okay. I'll make sure that everybody can see this, because this is where we're going to be editing. Okay? So everybody go into your flappy.py is the folder, the file we're going to be editing. So the top looks like this. So we're going to go all the way down to where it says this guy, initiate all models. So this is the thing. It says to do on it, and it says create the Keras model, add the model to the current pool, and reset fitness scores. Cool. So I'm going to start going from here. So first thing we need to do is create our model. So in Keras, we have a thing called a sequential model. It just means that everything is going to be, every time you add a new layer, it's just going to add on underneath, kind of like appending to a list, all right? So Keras makes it a little bit easy for us. Then we're going to add our first layer. Let me know if I'm going a little bit fast. I'll leave it up once I've coded everything so you guys can copy it down. But we have quite a lot to get through, and I kind of want to give you guys enough time to train your stuff. So our first one, so like we said in our ANN, it's all connected together. Every node is connected. In Keras, that's called a dense layer, okay? So we're going to add our first dense layer. And remember how Ryan went? We went over like what kind of, the three features that we're going to go into, right? It was the pipe height, length from the ground, length to the pipe, those three things. So our first input nodes, we're going to have 3, because there's 3 features we're putting in, right? So 3. We also have, there's like a weird thing called an input shape. Because we're going to be creating new models every time, remember how we're making a new brain every time from each 2 new birds? We have to tell it what kind of input shape it has. So let's put that in there. Got input shape. And we're going to say our input shape is going to be 3, just like this. Cool. Next piece, we're going to add our activation. So every time you add a new layer, you need to activate it so it goes and transforms it into that next layer, right? So our activation function we're using is called ReLU, which is rectified linear units. Like I said, you guys can read all about that. I'm sure there's a lot of YouTube videos and stuff on it, and all we just do is that, ReLU. We're going to add a hidden layer as well, which is going to be another dense layer. So like I said, you can go fancy with this. You can say like, oh, I want to do 8 or 7 or 10 or whatever one. Guys can be creative with this stuff. I just chose 7 because I like the number. A nice rule of thumb is if you take the number of nodes in your input layer and the number of nodes in your output layer and double it, that's like a good rule of thumb for your middle layers and the amount of nodes, okay? But there's no like set way to do it. So I'm going to put 7. That's just how I do it. I would recommend you guys doing that, otherwise stuff will break. So put 7 in there, and then we're going to also do that input shape function as well, okay? So it's going to be 3, just like that. And then we're going to activate this, the same thing. Activation function, and we're also going to give it ReLU. And now we're going to add another dense layer, and this is going to be our output layer. So remember, we're going to output either flap or don't flap kind of thing. So we only have 1. It's going to be 1 output at the end. And again, we need to put the input shape, which is the shape of the one before it. So it's going to be 7. All right. And don't worry, I'll leave this open for you guys so you can see what's going on, okay? Before I move to the next thing. Next thing, and now it's our last activation function. And this is called a sigmoid. This is like the oldest one you can possibly get, but seems to work when you only have 1 value, okay? Oh, let me get rid of that, sorry. I'll expand this for you guys. Okay, so that's kind of like how we're designing our model, okay? Model should be designed, that's how its structure is. Now we're actually going to compile it and make it actually a neural network. So this is called a function called model.compile. Just like this. We have a loss function, and this is like saying how bad it is. I don't know if you guys have taken stats classes. We're going to use the mean squared error, MSE. And I know I'm going a little bit fast for you guys. So read up on all these things if you're a little bit confused, and I can totally answer questions afterwards. We also have to tell it what optimizer, so what is the thing that's going to make it go towards that minimum error. So we say our optimizer is equal to, and we're using a thing called ADAM, which stands for adaptive momentum. You guys can totally read like 13-page research paper on that if you want. And then we're going to say we want to just get our metrics out, like how accurate it is. So all we're going to put in this little thing is, and I'll move it over, accuracy. Just like that. And I'll show you guys here in a minute. Let me do that. So that's our line right there. So, yeah. How's everybody doing? Dying? Yep. If you don't have to understand it 100 million %, copy it down. Okay? And I'll post the code for you guys if you want to copy it later. But this is kind of the most complicated part. This is the neural network part. This is where people get paid $400,000 a year to do. So if you're learning it in 3 minutes, good for you. Just copy down this stuff. All right. So the next part is we're going to add it to our current pool. So current pool, you don't need to worry about. It's just saying like these are all the models that we're going to be taking from all our birds, right? All our birds. We're technically making the brain. So we're now adding a new brain to the pool of brains that we're going to be taking for our birds, okay? So now we're just going to say append model. And the next thing, we're going to go fitness dot append. And we're just going to reset the scores. So this is what a fitness, I'm not going to go too much into. Fitness is like when we finish a game, we want to get the top 2 birds. Fitness scores are like how good they are. So if our bird gets to like the 4th pipe, and that's awesome, he was the top bird, his fitness score will be 4. So all we're doing is resetting so we can say like he had the highest score, let's take him. And then we're done here. We're done on this function. Let me know when I can move on, guys. I know it's a lot. I'm sorry. Everybody okay? Dying? Coolio. I'll leave it up for like another minute.
Can you scroll it up a little?
Yeah, sure.
Or like the other way? Yeah.
Like that?
Yeah.
I don't want to zoom in too much because it'll cut off like this
Yeah.
accuracy line. I can try.
Yeah, that works. And then probably zoom in a bit.
Guys all good? All right. So now we're moving on to our actual part where we take our 3 features and feed it into this model. It's going to be fun. So next piece is right here, prediction action. So move up a little bit, and we're just going to put this piece in right here. Everybody good? Yeah. Can you guys just raise your hands if you're not good and people come help you? But everybody seems to be okay. Alrighty. Alright, so next piece, we're going to actually take our 3 features, like our height from the pipe, height distance from the floor, distance to the pipe, and actually feed it into our neural net, okay? So we can just call it, I don't know, neural input. And you guys will learn that neural networks, so there's this thing called NP, which is called Numpy. It's like a neural network pre-processing library for Python. So just say NP, and it's like the shortcut. And we're going to go as array, just like this. And then we're going to make a list of the height. And we're going to say the distance from the pipe, like this. And we're going to do the pipe height. Don't worry, we defined them all for you guys already, so you just kind of have to slap them in there. Okay, so the next piece is we have to transform this little neural input array into a tensor. I know that sounds intense, hence Tensor Flow. It's kind of like a 2D array, okay? That's how all neural networks accept all their inputs. So you can't just like dump one single number in there. You have to expand it into a 2D tensor. That's why NumPy is so awesome. It makes it really simple to do that. So we're going to say neural input is equal to our numpy function. We're going to go at least 2D, just like that. And we're going to feed it our previous input, just like this. Pretty chill. All right. And now we're going to say, like, okay, now we want to actually feed it into our neural network and get a response back, okay? So now we're going to do, let's say, output probability is equal to, and we're going to do this for each one of our birds. So remember, our birds' brains are stored in current pool. So we're going to say current pool, and we're going to give it, which is an array of all the things, all the brains. And we say model number, just like that. And we're going to go dot predict. And then we're going to send it our neural input, just like that. And I will expand this so you guys can see it. Can everybody see that? What's up, buddy?
Did you define a threshold for, like, on the last layer for a threshold for the probability in order to flap, or?
Yeah, we're going to do that right now. We do that right now. So because we technically just fed our neural input in, we're going to get our probability out, and then we're going to show if our probability is over 0.5, we won't flap. If it's below 0.5, we're going to flap.
Wanted to check if we did that.
You're good, man. Keeping me on track. Thank you. All right. So like we're going to do that exactly right now. So if our output probability is less than or equal to 0.5, we're going to return 1, so flap. If it's not, return 2. Cool. How's everybody doing? I know this is complicated, guys. I know. When you guys get into like AI research, this is kind of the stuff you get to do. It's super fun and not frustrating at all. You'll love it. All right, I'm going to give you guys like a minute to copy this down. Let us, like I said, raise your hands if you have any problems. You don't have to understand the stuff like 1,000,000%. We have 6 more workshops. If you guys have any questions and any of that stuff, we can answer if we can, all right? How's everybody doing? Everybody all good? Can I move on? Alrighty. So now we're going to move up a little bit, and now we're going to actually create those functions for our crossover, right? Remember how Ryan went over the crossover? We're going to take the 2 parents, the 2 best birds, take their genes and like crush them together and create new ones. Cool? So first we just need to declare a global variable, which is going to be our current pool, just like that. And we're going to say weight 1 is equal to our current pool, parent 1 dot get weights. So this is like getting their genome, if that makes sense. Sounds really nerdy, but it is. Cool. And now we're going to do the same thing for the second parent, just get their weights. Cool. And now we're gonna, so now we have the genome, the genes of the both of the parents, so parent 1 and parent 2. Now we're gonna create new ones from those, okay? So we're gonna say new weight, new weight 1 is equal to, let's see, weight 1, like this. And then new weight 2 is equal to weight 2. And now we're going to select a gene that we want to cross over. So we're just going to say our gene is equal to 0, because we're going to take the first one. So these weights or whatever, they're just the weights of all the neural, like all the nodes of the neural net. So we're just going to take one and swap it over. Super easy. All right, so we're going to say new weight 1, this gene is equal to weight 2, this gene. And then new weight 2 gene is equal to weight 1 gene. And then we're going to return this as an array. So we're going to use that MP function again and send these back. And that's it. Yeah, sorry guys. Does that kind of make sense? I'm not sure if all of you guys have done Python before. This is Python, by the way. How's everybody doing? Okay? Yeah, anybody got questions at this point? Probably a ton. Cool. So we're going to move on. So once you guys have copied this down, we're going to move on to our mutate function. And then we're almost done. Then we're almost there. And there's like one more thing to do. All right. So if you scroll a little bit down, we got our model mutate right here. Did everybody get to copy this down, by the way? Everybody good? Coolio. So we get our mutate function right here. So this one's pretty chill. So we're going to cycle through every single one of the weights in the brains and every single one of the nodes, and then randomly change some of the values. So they're not all the same every time. So we have a nested for loop here. So for I in range. So the amount of layers in the weights, it's like this. And we're going to do another one for j in range. So first function loops through all the layers. Remember we had 3, and then the second loop loops through all the weights in each one of those layers. That makes sense? All right. So now we're going to do like a random function, because we don't want to change them like the same way every time. The whole point of mutation is that it's random. So we're going to like base it off a random number, all right? So we're going to go, so if random dot uniform, and we're going to choose a number between 0 and 1. And if that number is greater than 0.85, we're going to do some stuff. So there's a very small chance that this actually mutates. We're just going to give it a random value. So we're going to say we don't want to change it by too much. So we're going to say our change is going to be a random number. Same thing, random uniform. And it's going to be between negative 0.5 and 0.5. Cool. And then we're going to change the weight. So weight I j, and we're going to just change it like this. I'm going to add the change in, and then we're done. How's that, guys? Yeah, what's up, buddy?
How do you decide like how often you want a mutation to occur?
When we tried testing this out, we didn't want it too often. We kind of went with what the standard is. So in humans, this mutation is very little. So 0.85 was kind of like the chance of that happening. So we kind of went with that. It doesn't happen very often because we don't want them to be all over the place. They do want them to kind of keep like their like gene pool from the rest. We don't want it to be like, here's two parents, do the crossover, and then change them completely. We just want them to change a little bit. Cool. How's everybody doing? Good? We're on the last part. Then we can see some birds flying into poles. Cool. All right, last part, guys. So we're going to scroll up to this to-do here. Now we're actually going to call those functions that we just built right here. So it's to-do, perform crossover, and mutation. All right. It's really not that bad. So we're going to say our new weights. Just call it new weights 1. Oh, let's make that a little bit better. So crossover weights, because that's what we're doing, is going to be calling that function we just did. So model crossover, that function we just wrote, and I already set up. So if there's like 2 for loops right above this function, which collects the 2 top parents, and they have indexes, so we're going to send those indexes, idx1 and then idx2. So those are our 2 top parents. Those are the ones that perform the best. We're now going to send them and get their weights crossed over. So now we're going to mutate their weights. So we're going to say mutated 1 is equal to our mutate function. So model.mutate. And we're going to say crossover weights. The first piece. Because remember, crossover weights returns back 2 pieces in an array. So we're going to send the first piece to mutate, and then we're going to do the same thing with the second piece. Mutate 2 is equal to model.mutate, and we're going to go crossover number 1. All right. Sounds good? And then there's, the next thing we need to do is just add it to the next pool. So this is called new weights dot append, and we're going to append each one of those updated, both the mutated weights. And same thing. Cool. And that's it, we're done. Yay. So once everybody's got that running, before I pull it off, to run the function, I'll show you how to do it in a minute. I want to make sure everybody gets enough time to write this all down. You get to go Python. So in your virtual environment with it activated, you want to go Python flappy.py, and it should. The first run through takes a minute because it's creating all the stuff, but after that you'll see it'll go a lot faster. So is everybody good? Yeah, can I run the thing? Cool. All right. So now that we're in here, I'm just gonna go Python. Let me minimize this a little bit. So remember, you have to be in the folder. You have to be in the folder with all your stuff. In this Flappy Bird Workshop Master folder, and you have to have the virtual environment activated. All right, and we're just going to go Python flappy.py and see if anything breaks. So you can see Pygame's running, Tensor Flow's been activated. It's loading all our random weights. It brings up this tiny window. So remember, the first time takes a minute. Like the first time the birds run. So there they go. And so once it stops here, it dies. And once it's loading up new weights, it'll go a lot faster from now. So that first number is the score, and that second number is the generation. So this is generation 1. So like I said, the first time takes a minute. There we go. Yeah, look at them go. Sucks. Yeah, they'll be trash for the first. They take about like 25 to 30, but it depends. Yeah, look at it go. Yeah. Does everybody get this to run? Kinda? Yeah. What do you need to go back to? Oh, sure. You just run, so make sure the virtual environment is installed and activated.
How do we what's the command to access the folder?
Like CD, like
No.
the venv.
Yeah.
Oh, okay, so that is in your, that's kind of in your, that README folder? Are you on a Mac or Windows? Okay, so it's going to be, did you create it and install everything?
Yeah, I did everything.
Oh, just to activate it? Source, so you type in source, the name of the venv or whatever you called it, Flappy venv or whatever you called it, /bin/activate. So I'll come help you in a minute. So guys, this is the function right there, okay? So once you have your venv activated, just run this function. How many people got it to run? Yeah? Is it going? Do they suck? Or are they doing okay? Yeah, they're doing okay? Hey guys, want to thank you all for coming and everything. Let us know if you have any questions. I know this was super complicated. I will post this code up. We also have just like a few references that we got to show because, you know, we're students and stuff. So the code of the game, there's like a few GitHub stuff. You guys can go and check it out. But let us know if you have any questions and come back next week. You can talk to me right after. I'll be here for a while if you guys have any questions. But thank you so much for coming. Hope you guys had a good time. I actually got to build something. All right, thank you.